The goal of this video is to understand the precise definition or what we call the epsilon-delta definition of the limit. It is a difficult topic for some students, so let's see whether we can make sense of it. Suppose we have a function fx and a point a which may or may not be in the domain of the function. So then we're gonna say the limit when x goes to a fx equal L if fx gets arbitrarily close to um, close to L, arbitrarily close to L, if, or we can say when x gets arbitrarily close to A. So this is what we are if this happens, that means if fx gets arbitrarily close to L when x gets arbitrarily close to A. So this is what we mean by the limit, but this is what we normally call the informal definition. So what we're trying to do is we try to represent this idea using the epsilon delta definition. But before we do that, let's look at a graph. So let's say we have a function and then so this is A. So function may not be defined at A, so we remove that point, and so this is the value L. So this is the x-axis, these are all important, x-axis, and the y-axis, and this is a function y equal fx. Now you want to make sure that you can make the function value as close as to L by making x as close as to A. For example, let's say so you pick a value y, so that's the value y, so you can find the corresponding value by mapping the function. So you can map to the x-axis. So that means if you start with the x1 value, you're gonna end with the y1 value. So let's see whether let's find a value which is much closer to that. Let's say, for example, we're gonna pick y2, which is much closer to L, and then the corresponding value of x is this one. So you can see that these are close to A. So those are the values larger to L. What about the values which are smaller? For example, we can find a value below L. So for example, this value. So you can see, and the corresponding value you can map. So that's the x3 value which gonna map to y3 value. So and then you can see that, so if so this guarantees that if you stay close to A on the x-axis, and you can see that the y value stays close to L. But the problem is you cannot just pick like 1000 points like that and so that yes it works, because that's not like a correct proof, because we have we don't know what will happen if you pick another point. So the idea is to pick random points. So you just pick a random point which is close to L. To do that, what we're gonna do, we're gonna map the whole neighborhood. So what we call the neighborhood. Neighborhood means the values close to L. So we're gonna pick a value close to L. So we're gonna pick a neighborhood of L. So to do that, what we do in mathematically, we pick a interval. For example, what we're gonna do, we're gonna go what we call the epsilon distance from the y-axis. So we're gonna start with L and then go epsilon distance both ways. So let's say you're going to go epsilon. So you really don't need to go the exact equal distance, but just to make the writing easier, we pick equal epsilon. So you can pick epsilon 1 and epsilon 2, but rather doing that, we can pick the exact same one because it's much easier to write. And then so you go up epsilon, this is just a positive number, and then we also go down epsilon. So when you do that, what happens is it's going to create an interval. So it's going to create this interval. So there's a ending value. So this is L minus epsilon because you go down. So it's L minus epsilon. And then if you go up, so this is L plus epsilon. L plus epsilon. So that means, so you want to make sure that your value is, so this epsilon can be any smaller value, so that it can be very small. So that's what we call arbitrary small. Arbitrary small. Arbitrary means epsilon can be any value. Okay, so epsilon can be any value. So that's how we transform this arbitrary word. So any epsilon positive, because it will be like a because that's a radius, so it will be positive value. And then what we're gonna do? So then we see what is the corresponding region on the y side. So we can trace back. So we can trace back. So if we trace back, so this is what happened. And then it's going to map down to the x-axis. And then the other side, so you can see you're going to map. And then, so that's the other side. So those are the two values. So, and those are the corresponding values. So we have a larger one and a smaller one. And you can see that, so these are what we normally call the delta. On this side, we call delta. So we have delta 1 and delta 2. So in general, those deltas are not the same. So they are different. It's depend on the graph. So if graph has a larger slope or a higher derivative, what will happen? The delta is smaller because it increases much faster. So that means you don't need much changes in the x direction to get that variation on the y direction. So that means delta is smaller if the derivative is larger. Delta is larger if the derivative is smaller. So now what we're going to do is, out of those two deltas, we're going to pick the smaller one. Out of those two, we're going to pick the smaller one. So once you pick the smaller one, so in this case, delta 1 is smaller. Now we just use this idea here. So delta 1 is smaller. So what we can do, we're going to map delta, we just get a delta 1 interval, or that we call delta 1 neighborhood. So what are those values? So you can see this value is, so a smaller one, so it's going to be A plus delta 1 on this side. On the other side is, it's going to be A minus delta 1. So that means we can write this interval. So what is this interval? So what we can do, we can find any value on this interval. In other words, you can see you go delta, or let's call it just delta in this case. So it's much simpler. So you can see you can write this interval. That's an interval. So it's, you can see that those all the x values are delta away from a. So that means it is simply, you can see it is the distance between x and a has to be smaller than delta. So that's where the x minus a less than delta coming from. And also we do not worry about what happened at a, because at a function may not be defined. So that means we want to guarantee that we do not consider x equal a situation. So to remove a, what we can do, we're going to say this is 0 less than x minus a. We write it like that. Once you do that, it's going to remove a. So that's remove a. Good. So now let's see what happened in the region. So now if you look at this region, that this new region, you can see, look at this region. So that's the region we are talking about here. So in this region, and then you can see if you map this from to the function, and you can see it's going to map right here. So it's going to go there. So that is the region we have. So we have this. You can see it's not symmetric. Now there's a very important thing happen here. You can see that if you start with the delta neighborhood, what we call delta neighborhood of A. So that means on this interval, if you start with on this interval, and you can see that the y value is stay on uh, this interval. So you can see a y value only maps to this, but you can see that that's within the epsilon neighborhood of L. So you can see that there are no values below, but you can see that the interval is inside the epsilon neighborhood of L. So in other words, so what's epsilon neighborhood? So you can see that that neighborhood you can write as the gap between the function and the L value is smaller than epsilon. So that is the neighborhood, epsilon neighborhood of L. But you can see that the actual function value is sitting inside that interval. Uh, so the larger interval, actually you can write it like this. So you can see, if you look at the larger interval you can write like, so it is from L plus epsilon to L minus epsilon, and you can see that, so that's the large interval, and you can see that uh, the the function value, the interval of function value is sitting inside that particular interval. So that means it's missing a part, but it still is inside the interval. So and then you can see that, so if you start with the delta neighborhood of A, you can see that the function is sitting in the epsilon neighborhood of L. So that is the idea of the delta epsilon definition. Now how we can write this, and you can see that delta depend on the epsilon value. So once you get the epsilon value, delta depend on that. So that means, and also we know that the delta is epsilon is an arbitrary value. So that means delta can be any smaller value. That's why we say for all epsilon, so any arbitrary value. So how we can write it now? So what we can do, we can pick any epsilon. So that means, that's why I say for all epsilon. So once you pick epsilon, that means you pick any random epsilon, and then that's gonna give you the corresponding delta value. So there is a corresponding delta value such that for any function value, any value in the domain of the function, if x is sitting in the delta neighborhood of A, that means x is within delta from A, and also is not equal to A, then it guarantees that, or implies that, the function value is in the epsilon neighborhood of L. So that's where those epsilon delta definition coming from, and you can see that it's very clear from the graph. So that means you're gonna guarantee that you're gonna pick a delta. So if you start with the delta neighborhood of A, and you guarantee that the function value is sitting in the epsilon neighborhood of L. So it may not cover the whole interval, but it will at least cover part, but that part is inside the um, epsilon neighborhood. So that's the idea of the limit definition. So let's try to see this through an example. Now let's look at this problem. So consider the piecewise function fx equal x plus 1 square root if x are not equal to 3, it is 4 if x equal to 3. So what does the graph looks like? So you can see that so the graph gonna look like this. So this is shifted to the left by 1. So that means, and the square root function, so it's gonna be like this. like that. So that's the x-axis and the y-axis. So this is -1 and 0. So the value 3 are not up to scale, so it's here. So let's say this is 3. It's not in a scale. Okay. So and you can see that so there's a hole there. Um, so function looks like this. Um, and then at 3, so the value is 2. So at 3, so the value is 2. So that's the value 2. And then you can see that the close to the value 3, the function get close to 2. That's 2. It's not any scale. So what we're gonna do is, so we're gonna pick a neighborhood around 2. So what we're gonna pick epsilon neighborhood, that's what we normally call around 2. So let's say, so we go epsilon distance away from 2. So that means so this is 2 plus epsilon, and this is 2 minus epsilon. So we go epsilon away from 2. Now we're gonna find the guaranteed neighborhood around 3 that's gonna map all the values to this one. So what we're gonna do, so you can find those delta values. So one value is here. So that's gonna be one value, and the other one is there. And you can see that those two values are not the same because they have different slopes. So when there's a slower rate, the delta will be large. Good. So now, and you can see that, so this is smaller one, so we're going to use the smaller one. Because once you pick the smaller one, it guarantees that it's going to map everything back to the interval. So that's the interval we're going to pick. And so that's the corresponding values. And you can see in this region, so that's the region we are interested in this case. And you can see, so if you start with any value in this neighborhood, if you start with any x value, so that's x value, any x value in this neighborhood, and you can see it's guaranteed map inside the epsilon neighborhood of 2. You can see that's where it's. So that means, so we need to find this value. So that so there are two delta values. So that's a optimum value here. So to find the optimum value, what we can do is we can find the corresponding x value here. So there's x1 value corresponding. So we can find that value, and then we take the difference. So that difference are going to give you so the delta value. So that's the smaller delta value, and this is the larger delta value, and then we're going to pick the smaller one. So to find x1, what we can do is you can see you can plug in that the function. So what we have is so that so what we need is x plus 1 square root should be equals to 2 minus epsilon. That's the value we are looking for, the bottom value, because that's the closer one, because the other one is like far away. So and then you can square this, and then you can write this one as x plus 1 equal 2 minus epsilon squared, and then x1 in this case is 2 minus epsilon squared minus 1. So now the delta 1 in this case, or delta, so I'm going to call it delta 1, and you can see that that is the gap between 3 and x1. So this is simply 3 minus x1, and you can see that this is 3 minus x1 is 2 minus epsilon squared minus 1. And if you simplify, what happens is you can see so you're gonna get so you will get 3 minus. For a problem like this, we had to do some work to find the the delta value. So we normally call those a rough work. So how we do it? We can start with the what we need to prove. So we need to prove that fx minus 2 is less than epsilon. That's what we are waiting for. So we plug in the function here. So so we can say x plus 1 square root minus 2 less than epsilon. And then your goal is to come up with a term x minus 3 absolute term. So that's what we are waiting for. We are waiting for this kind of term, x minus 3 absolute value less than something. So what we can do is we're gonna to do that we're gonna multiply by the conjugates inside. So when you do that, so let's say so we have x plus 1 square root minus 2 times you're gonna multiply by the conjugate. So which is x plus 1 square root plus 2 divided by x plus 1 square root plus 2, the absolute value of that. So this is less than epsilon. That's what we want. And then using the difference of the squares, you can see that this can be x plus 1 minus 4 divided by, and you can see the bottom this is always positive, so we're going to write it like that. Plus 2 less than epsilon. So that's what we want. And you can see this simplifies to x minus 3 at the top. In the bottom, I'm going to write the bottom like this just to exaggerate something here. So we have plus 2. So the goal is to, and then it has to be less than epsilon. So the goal is, what we can do now is we can find the largest value of this expression. Find the largest value. So when you have the largest value, so what you can do, you can write this. So we can write, we can say if you pick the largest value, so let's write it here actually. So I'm going to take it out. So you can say this is less than or equal. Now you replace the largest value here. So this is less times the largest value of this expression, because you can see in the bottom you have x plus 1 square root, which is always either 0 or positive. It's a non-negative term. That means you are adding something either 0 or positive. That means it's going to get smaller when you add that. That means the largest value has to be 1/2. So that means times 1/2. Now what we're going to do, we're going to make this smaller than epsilon. So we're going to do. So now this is going to give you an expression, and you can see that when you multiply by 2 both sides, you can isolate the x minus 3 term. So when you multiply by 2, you're going to get 2 epsilon. So now you can see if you pick this value as the delta value, and then you can see you can reverse, you can write it backward, and you're going to end up with the with what you need to prove. So that's exactly the idea. So you're going to call either this value or anything smaller than this as the delta. So you don't need to pick exactly this value, but this is one option. So what we normally do is, so let's pick something smaller. So in general, what you can do is, so you're going to pick something which is smaller than, so that's the delta, which is either less than or equal to 2 epsilon. And then you can see that's going to work very well. So we found the value, so it should be either 2 epsilon or anything smaller than. So you can even say like epsilon, just epsilon, or half epsilon, or epsilon or 10, something like that, but it has to be smaller. So that's the point here. So you can pick anything smaller than 2 epsilon, and let's see how to write the complete proof now. So this is just a rough work, and then you found the epsilon. Now what we can do, we can write the answer backward. So let's write that completely now. So now in the proof, you want to make sure that you pick any random epsilon value. So to do that, what we can do, we don't put in restriction, we just say let epsilon be positive. So just any epsilon value, and then we're going to say choose delta equal to epsilon, and then you can see which is positive. So now what we can do, we can say suppose 0 less than x minus 3 less than delta. So then what happened? If this is the case, that means if you pick any such value, you can see that this guarantees that x minus 3 less than, we know that delta is 2 epsilon, so we can replace by 2 epsilon, which is delta. Now what we can do, we can divide both sides by 2. So we can write this one as x minus 3 divided by 2 less than epsilon. And then since 1/2 is the largest value, what we can do, we can replace this one by x minus 3 over x plus 1 square root plus 2 less than epsilon. Now what we can do is we can multiply, we can simplify this one. So to simplify this one, we can again write the top as the using the conjugates. So we can write this at the top, you can write as x plus 1 plus 2 times x times x plus 1 square root minus 2, and then divided by x plus 1 square root plus 2. So you know that from the rough work, this is exactly what happened. Those are terms that you're going to get, which is less than epsilon. And then you can see this terms get cancelled, so you're going to get a term get cancelled out. So this simply says that, so this implies that x plus 1 square root minus 2 are less than epsilon. And since we pick any epsilon here, and then this proves the condition. Then to complete the proof, you can say therefore for all epsilon their x is delta positive, their x is delta positive, such that for all x in the domain of the function 0 less than x minus 3 less than delta implies x plus 1 square root minus 2 less than epsilon. So that's going to complete the proof of the limit. So this is how you prove the limit using the epsilon delta argument. So let's look at several practice problems in another video.